Right, I'm halfway down the mountain. Stunning view over there. So I'm just about to go into Plan Village, which is basically a straight run through. My plan for this one, excuse the pun, is to determine the frictional coefficient of ice, snow, or rather skis on snow, by determining my altitude drop, how much speed I should achieve, what's lost in friction, and so on. So here we go. I'm just going to put geo tracker on and try not to put the brakes on either. Okay, see you in a bit. So hi there, we've got a little diagram of the ski slopes, greatly simplified because it's assuming the slope is constant. We've got the geo-tracker information on the left hand side. So what we're looking for is some information that we can use. So we have a track length of 936 feet, okay? So that's from start to finish. Obviously being in feet is not ideal, so S I'm going to put as 936 feet. Well, if you just do a sort of a rough estimate of about 3 feet per metre, it's roughly equal to 300 metres. Okay, so there's our distance. We've also got a maximum speed, so that is basically the speed at which we hit the bottom of the slope. Now I'm assuming that that is the speed I would have reached had I not put any brakes on or done any turns. I tried not to. I can't say that is the case, but we're going to use V as equal to 16 miles per hour. Okay, which in terms of meters per second, what we're after is going to be, we've done some calculations on this before, it's about 4/9 of that, okay, which is going to be equal to 0.4 recurring, so I'm just going to do roughly 0.44 times 16, so we're talking about 7 meters per second, so there's our rough estimate for the maximum speed that we reached. You can see the speed chart actually consistently increases here, which is encouraging because it shows that it's a uniform acceleration, so therefore a uniform force of resistance, which is the frictional force we're looking at. And down at the bottom we have an elevation chart, but we're just going to use the vertical distance, which is going to be 31 meters. So I'm just going to say that H is approximately equal to 30 meters. Once again, a little bit of an estimate. So, in terms of energies, what's going on? Well, we know that the gravitational potential energy gets converted into kinetic energy plus whatever work done is against friction. We call that W subscript F. Okay, may look a bit more like an F than it does. Maybe. Okay, so work done against friction is what we're actually after, and then from that we can actually work out the force of that friction and therefore the frictional coefficient. Okay, so let's use what we know in terms of mgh is a half mv squared plus, and we're going to say F, work done against friction times S, which is actually our 300 meters. Okay, now let's just look at our diagram. Now a little bit further down in my geotracker data, it tells me that there was an average slope of 10 degrees. Okay, so I'm going to use that. I'm going to put some annotation on my diagram. So what we do know is there's an mg acting downwards. Okay, I also know at 90 degrees there's a normal reaction force, we call that R, and against this we have F equals mu R, which is our frictional force, and mu is the value we're looking for, the frictional coefficient of snow, or skis on snow. So if we continue our triangle here, this is the angle 10 degrees, which is going to be the same as our slope angle. So this little force arrow here corresponds to mg cos 10. Okay, and that actually is equivalent to our normal reaction force because it's in the same line. So we have mg cos 10 is our value of R. Okay, so if we plug things in here, we have mgh equals a half mv squared plus F times S. Well, F is mu R and R is mg cos 10, so this becomes mu mg cos 10 multiplied by S. Okay, so we'll put the S in front. Okay, now you'll notice conveniently that right across the board my m's cancel, so this is independent of mass. So we're now left with an equation we can simplify. So remember, we're looking to make mu the subject. Okay, so we can basically subtract half v squared, so we end up with gh, take a half v squared, okay, and then divide through by sg cos 10, leaving mu on its own, okay, sg cos 10, okay, and that's going to be our value of mu. Okay, so we've got all the values we need. All we now need to do is plug things in. Okay, so we've done the hard work. All that's left for us to do now is just sub everything in. As with all my calculations, they're I call back of the envelope calculations, so some sort of estimates to make our lives easier. Because of course there's a lot of things that we haven't considered. So rounding up and down will actually not necessarily massively affect our calculations. So we've now established a relationship between mu, the frictional coefficient of snow on skis, or skis on snow, and the parameters that we recorded, and also the value of g. So if we just plug things in, on the top we get gh. So h was, I haven't written this down, about 30 meters. Okay, so gh is going to be 10 times 30 minus a half times v squared, so that's 7 squared, all over sg, which is 300 times 10, and then multiply that by cos 10, which is approximately 0.98, it's more or less 1 actually. So I'm quite literally going to cancel a few things down, so we get 300. I don't like using calculator, so I don't have to. A half times 7 squared is roughly 25, because 7 squared is 49, half of that is 25. All divided by 3,000, and I'm just going to call this 1, so I'm going to cancel that through. All divided by 3,000. Oops, my zeros are overlapping a little bit. So mu is approximately equal to 300 minus 25 is 275 over 3,000. Okay, now if I tap that into a calculator, I really want a decimal value, because frictional coefficients are usually given as decimals. So here we go, 0.092, or approximately equal to 0.1. Okay, so you'd expect it to be low, because that's the whole purpose of skiing, sliding down the mountain. And I'm now going to look that up and see if it corresponds to an accurate value. Hi, so I've literally just been rooting around on the internet to look for the frictional coefficient of skis on snow. There's a variation of published values depending upon the condition of the snow, temperature, and the condition of the skis, and so on. But of course, that's a whole kind of a PhD waiting to be written. So I'm just going to go with what I found. So I discovered that the kind of most commonly published value was anything between 0.05 and 0.1. So that was our frictional coefficient range of skis on snow. Obviously, we're at the top end of that, but considering we did a few simplifications and so on, that's well within our parameters. Okay, so once again, physics and applied maths seem to have done a very good job of that. So thank you.